Today, we will talk about the basic of electricity and how it works. Now, I will show you a short video clip of the basic of electricity.
Electricity. Have you ever wondered what electricity is and where it comes from? In this video, we are going to talk about electricity found in nature, called lightning, and man-made electricity like batteries, power plants, and more. Electricity found in nature is called lightning. Lightning is an electric current and is super hot, even hotter than the surface of the sun. Lightning occurs when small bits of ice bump into each other as they move around in a cloud together and create an electric charge. When the cloud fills up with these charges, it interacts with the opposite charges on the ground, kind of like the positive and negative sides of a battery. Lightning strikes, and you have an electric current. Electricity is all around us. Think about a day in your life and all the things you use electricity for. Would you be okay living without these things? But what exactly is electricity and how does it work? Are you ready for an introduction to electricity? Electricity is created when electrons move from one atom to another. When the electrons are moving, they produce something called an electric current. There are two types of electric currents: direct current and alternating current. Direct current is the power that comes from batteries, fuel cells, and solar cells. Batteries have a plus and minus sign on them. The plus sign stands for positive, and the minus sign stands for negative. The electric current in the batteries always flows in the same direction and in a loop from the positive to the negative side. Batteries power things like game controllers, flashlights, phones, even the TV remote we fight over. Fuel cells also work like batteries, except they don't need to be recharged. Fuel cells take chemicals like hydrogen and oxygen and put them together. When the two chemicals react to each other, or have a chemical reaction, electricity is created. Fuel cells can provide power for something as big as a utility power station to something as small as a laptop computer. There are even hydrogen-powered vehicles that use fuel cells. Some of these vehicles include forklifts, cars, boats, and buses. Have you seen solar cells on the roofs of various homes and buildings? Maybe you even have some on your own home. They look like black rectangles made of glass. The materials inside the boxes release electrons when light shines on them, which then creates an electric current. Can you guess where the light comes from that shines on these boxes? If you said the sun, you're absolutely right. Solar cells use the light from the sun to make electricity. There are some important words that have to do with electricity. These words are watts, or how much power a light is using; voltage, how much power is available for the light to use; and amps, how fast the electrons are traveling to the light bulb. Shorter, longer, thicker, and thinner wires also affect how electricity travels. Shorter and thicker wires allow for better flow of electrons than thinner and longer wires. Now, let's learn about alternating current. Alternating current is an electric current that reverses directions many times a second. This power comes from power plants. The electricity travels through the power lines that you see along roadways and open fields. The electrons travel in a big loop from a power plant to the wires that are hooked up to your house, and then back to the power plant again. When you turn on a light in your home or plug something into an electrical outlet, the power flows from the power plant. But Before it enters your home, it passes through something called a transformer. Nope, not that kind of transformer. That would be really cool, though. Transformers are attached to the utility box or power poles near your home. The electric current flows from the transformer to the circuit breaker or fuse box in your home. That fuse box then routes the electric current to each of your outlets and switches. The transformer's job is to make sure that the right amount of power is going to your home. This is a very important job. If too much electric current flows all at once, it could blow a circuit and cause all the appliances in your home to stop working. And if too little current flows, it won't be enough to power all of your appliances. Power plants all over the country use different kinds of fuel to produce electricity. Thermal power plants use coal, biomass, petroleum, or natural gas to heat water into steam. That steam then powers a generator which produces electricity. Isn't that amazing that hot water can produce electricity? Nuclear power plants use fission, which means splitting atoms. Splitting the atoms creates energy, which produces heat, which also creates steam. Geothermal power plants use the heat located inside the earth to create the steam. And hydropower plants use wind and moving water to create the steam. Electricity can also be produced by magnets. Can you guess why? You already know that electricity is created when electrons move from one atom to another. But did you know that a magnetic field can move electrons? Power plants use giant magnets to create electricity in a generator. The generator has a coil of copper wire inside the magnets. Steam makes the generator spin, causing the electrons in the copper wire to flow through the power lines. Another type of electricity you are probably familiar with is called static electricity. Have you ever been shocked when you touched a doorknob after walking in socks across the carpet? That's static electricity. It happens when electrons move from one place to another, like from your hand to the doorknob. Electrons can move more easily in some objects than in others. And when certain materials rub against each other, like your socks and the carpet, they transfer electrons. Another example of static electricity is when a balloon is rubbed on your hair. You might have tried this trick before. It's fun. The balloon picks up extra electrons, which then attract your hair to the balloon. This causes a literal hair-raising experience. The name for any material or substance that allows electricity to flow through it is called a conductor. Conductors include metals like steel, copper, iron, gold, and silver. But water, animals, trees, and even people can be conductors too. That's why you should stay inside during a lightning storm. You do not want an electric current flowing through you. Insulators, on the other hand, are the opposite of conductors. So, if conductors allow electricity to flow, then what do you think insulators do? They block or prevent the flow of electricity. Examples of insulators include plastic, glass, porcelain, and rubber. Most electrical wires are covered in a plastic or rubber coating. Can you guess why? What do you think might happen if you touched a wire that wasn't wrapped in an insulator? If you said you could get shocked, you're absolutely right. It's important to never touch any wires that you see. You never know if they are alive, which means that electric current is flowing through them. The plastic or rubber is used as insulators to prevent the electricity from traveling into other objects, like yourself. So, where did electricity come from? Electricity wasn't invented by anyone. It's a form of energy that occurs naturally. However, it is believed that the ancient Greeks first discovered static electricity in 600 BC. And in the 1930s, archaeologists discovered ancient batteries that may have been used at Roman sites. I wonder if those would power my controller. People have been doing experiments with electricity for years. You may have seen images of Benjamin Franklin, who was one of America's founding fathers, experimenting with electricity. A kite, a key, and a storm. Benjamin Franklin proved there was a connection between lightning and electricity. He was a pretty smart guy. There is much more to be learned about electricity. But what we do know is that without it, life would be much different for many people. Now that you know more about electricity, see if you can figure out these riddles. A group of birds are sitting on the power lines near your home, but none of them get shocked. Why? If you said it's because those wires are wrapped in an insulator, you're correct. Insulators like plastic and rubber prevent the flow of electricity. But even though they are wrapped, those wires still aren't safe to touch. If you ever see one down on the ground, don't touch it and get a grown-up. Ready for another riddle? I am incredibly hot, hotter even than the surface of the sun. I come from the sky, and when I connect with the ground, I make a big zap. I have electric current, but I am not used to power your electronics. What am I? Did you guess lightning? Well done! Remember, electric current in nature is called lightning, and the electric current in our homes is produced by power plants, solar panels, batteries, and more. Here's your last riddle. When you put our positive and negative sides together, we stick. But if you flip one of us over, we push each other away. We are used to generate electricity in power plants, but also stick pictures of you to your fridge. What are we? I bet you said magnets. Well done. Now that you are an expert about electricity, share some of these fun facts with your family and friends. Isn't electricity fascinating?
Now, I'll show you another video clip of how electricity works.
In this video, we are going to be looking at how electricity works. Now, this is pretty essential knowledge for any engineer, so we'll run through the basic parts of what you need to know. So let's start at the very basics, and for that we need to take a look at the atom. Everything, including you, is made from atoms. All the materials we use are made from atoms. The materials are just different because the construction of their atoms are slightly different. The atoms are made from 3 particles, 2 of which are found inside the nucleus, and the third particle sits outside this. At the center of the atom we have the nucleus. Inside the nucleus we have the neutrons, which have no charge, and we also have the protons, which are positively charged. The neutrons and the protons are much heavier than the electrons, so these will stay within the nucleus. Surrounding the nucleus are different layers of orbital shells. These are like flight paths for the electrons. The electrons flow along these flight paths, much like a satellite orbits our planet, except that the electrons travel at almost the speed of light. The electrons are negatively charged, and they are attracted to the positive charge of the protons. The electrons orbit around the nucleus in these orbital shells, and there are a set number of how many electrons can be in any one orbital shell. The number of protons, neutrons and electrons an atom has tells us which material it is. Atoms hold on to their electrons very tightly, but some materials will hold on to them more tightly than others. The outermost shell is known as the valence shell, and in this shell some materials have loosely bound electrons which can flow to other atoms. Atoms which can pass electrons are called conductors, and most metals are conductors. On the other hand, atoms which do not have free electrons and so they can't pass electrons between other atoms are known as insulators, and these are things like glass and rubber. Now we can combine these materials to safely use electricity by having the conductor in the center, which allows electrons to move, but surround this with an insulator to restrict where they can flow to, i.e. not into us, which keeps us safe. If we look inside a slice of copper cable at the free electrons surrounding the nucleus of the copper atom, you'll see that the free electrons are able to move to other atoms, but this happens randomly in any direction. If we then connect the slice of copper cable to a closed circuit with a power source, such as a battery, then the voltage will force the electrons to move, and these will then all flow in the same direction to try and get back to the other terminal of the battery. When I say circuit, this just means the route which electrons can flow along between the two terminals, the positive and the negative, of a power source. So we can add things into their path like light bulbs, and this means that the electrons will have to pass through this in order to get to the other terminal, and so we can use this to create things such as light. The circuit can even be open or closed. In a closed circuit, that means the electrons can flow around, and in an open circuit, this means that the electrons are not able to flow. Voltage is a pushing force of electrons within a circuit. It's like pressure in a water pipe. The more pressure you have, the more water can flow. The more voltage you have, the more electrons can flow. But what does a volt mean? Well, a volt is a joule per coulomb, and a joule is a measurement of energy or work, and a coulomb is a group of flowing electrons. We'll have a look at what a coulomb is in just a second though. So a 9-volt battery can provide 9 joules of energy in the form of work or heat per group of electrons that flow from one side of the battery to the other. In this case, the current of electrons flow from one side of the battery through the LED light bulb, which produces light, and then the electrons flow to the other side of the battery. Therefore, 9 joules of light and heat is produced by the light bulb. Current is the flow of electrons. When a circuit is closed, it means electrons can flow, and when the circuit is open, no electrons will flow. We can measure the flow of electrons just like you can measure the flow of water through a pipe. To measure the flow of electrons, we use the unit of amp. 1 amp means 1 coulomb per second, and 1 coulomb is a group of electrons. The group is incredibly large and is approximately 6,242,000,000,000,000,000 electrons, and that has to pass in 1 second for it to equal 1 amp. That's why electrons are grouped together and just called amps to make it easier for engineers. Resistance is a restriction to the flow of electrons in a circuit. The wire which carries the electrons will naturally have some resistance. The longer the wire, the greater the resistance. The thicker the wire, the lower the resistance. The resistance to the flow of electrons is different for each material, and the temperature of the material can also change the resistance to the flow of electrons. Electrical circuits use specially designed components known as resistors to purposely restrict the flow of electrons. This is either to protect other components from too many electrons flowing through it, or it can also be used to create light and heat, such as in an incandescent light bulb. Resistance occurs when electrons collide with atoms. The amount of collisions is different from one material to another. Copper has a very low collision rate, but other materials such as iron will have much more collisions. When collisions occur, the atoms generate heat, and at a certain temperature the material will then start to produce light as well as heat, which is how the incandescent lamps work. When a wire is wrapped in a coil, it will generate a magnetic field as the current passes through it. The cable will naturally create an electromagnetic field by itself, it's just intensified by the coil. By wrapping it in a coil, the magnetic field becomes so strong that the magnetic field starts to actually affect the electrons within the wire. But we'll look at why this occurs in a future, more advanced video. We can increase the strength of the magnetic field simply by wrapping the coils around an iron core. We can also increase the number of turns within the coils, and also we can increase the amount of current passing through the circuit. Now this is how electromagnets work, and it's also the basis of how induction motors work. If you want to learn more about induction motors, we've already covered this in another video already, just see the link on screen now. Now when a magnetic field passes across a coil of wire, it will induce a voltage in that wire caused by an induced electromotive force which is pushing the electrons in a certain direction. If the wire is connected in a circuit, then this electromotive force will cause a current to flow. This is the basis of how AC generators work, and the electricity at your wall sockets within your home is produced in a very similar way. Transformer. Now we can combine all of the aspects together that we've just covered, and when we do so we'll see that we can use one coil to generate electricity, and then we can place two other coils in very close proximity to each other but not touching, and this will create a transformer. The transformer will induce a voltage from the first or the primary coil over into the secondary coil, and this will force electrons to flow if the coil in the secondary side has a closed circuit. Now what's important about the transformer is that we can increase or decrease the voltage between the primary and the secondary coils simply by changing the amount of coils on either side. Again, this is a subject all by itself, so we'll cover this in a more advanced video later on. Now something else which I just want to briefly mention is the capacitor. So a capacitor forces positive and negative charges to separate across two plates when it is connected to a power supply. This causes a build-up or store of electrons within an electric field. When the power supply is cut or interrupted, these charges will then be released, flow up and meet again. This provides a power source, but only for a few seconds until the charges have paired back up again. It's slightly similar to a battery, but capacitors are very common and they're in almost every single circuit board. We'll cover this obviously in more detail in a future video, just be aware of these. So the last part I want to cover in this video is that there are two types of current electricity, that being alternating current or AC and then direct current or DC. Alternating current simply means that the current flows backwards and forwards in a circuit as the terminals are constantly reversed. This is a bit like the tide of the sea. It goes in and out, in and out, in and out, so that it's reversing constantly. Now alternating current is the most common source of power, and the plug sockets in your homes and your buildings and schools and workplace, etc. These will all be providing alternating current, AC. Now on the other hand, we've got direct current or DC, and that simply means that the current flows directly in only one direction. It does not alternate. This is what's provided from batteries, and almost all your handheld devices are from this as well. So we can convert AC to DC and vice versa using power electronics, and this is how we charge and power small devices, and it's also how solar panels can be used to power our homes, because solar panels produce DC power and our homes need AC power, so we have to convert this for it to be usable. So both AC and DC have pros and cons to it, but for sure we'll look at this in another later video. It's a bit more advanced. And there's also quite an interesting history behind why we use AC and DC and the inventors behind that. If you've got 10 minutes, I'd definitely recommend having a Google or a YouTube of this too.